Hello, my name is Syed Tabatabai, and this is my Lab 5 report presentation for Faraday's Law and bar magnet, which I'm going to be walking you through. In this lab, we will be dropping a bar magnet with the north end facing down, which then falls through an aluminum foil tube. We will model the interactions computationally and compare the results using Faraday's Law and Newton's second and third law, which state time-varying magnetic fields produce electromagnetic fields that can create a current in the conductor, in this case is the aluminum foil, and the fall of the magnet provides a time-varying source of magnetic field which then indicates a current that goes around the tube. There's 5 main laws that we're going to be using during this procedure. The first one would be Beer-Savart law. The second one would be Faraday's law, which states that changing magnetic field can induce a current in the surrounding objects. In this case, the current flows through the aluminum foil. You can see that theta equals B times A, the electromotive force equals N times d theta dt, and V equals IR. We're going to be using Newton's second law, which states that force equals mass times acceleration, and Newton's third law, which states for every force there's an equal and opposite force. In addition to that, lastly, we're going to be using Lenz's law, which states that the induced current will flow in the direction where the magnetic field will oppose the direction in the change in flux. For this procedure, we're going to be using our smartphone, a bar magnet, aluminum foil roll, and a meter stick. The experiment starts when we use the magnetometer app to determine which end of the bar magnet is north, and then held the tube of aluminum vertically and dropped the magnet with the north end facing downward. We also had to obtain the overall geometry of the tube and the magnet. The length of the tube came out to be 30 centimeters. The inner radius is 0.01 meters. The width is 0.015 meters, and the mass of the magnet is 0.023 kilograms. The average falling time over 5 different tests was 235 seconds, and the computational model results was 2.532 seconds. These are the 5 different results I obtained from physically doing the experiment and recording it using my phone and looking at the timestamps on the phone and basically getting an average of those 5 data points that we're going to be using in this experiment to compare the results with our computational model. And this is my code for the computational lab. In the first part, I added the geometry of the tube, and I also used the results from lab 3 and the mass of the magnet to define the characteristics of the magnet. Then I proceeded to define the magnetic field and flux, which you can see on the right, and at the end, using those computational models for the magnetic flux and the magnetic field, I found out the magnetic force on the ring, and using Newton's second and third law, I set that equal to the gravitational force acting on the bar magnet, which are equal and opposite, and at the end I calculated the time that the magnet would take to fall through the tube completely, using all the concepts that we used in this experiment and we learned about. And this is my closed grid model that I coded. You can see the graph underneath. There's an initial dip in the velocity of the magnet, and then after that kind of has a stable trend to it, and at t equals 2.532 is where the bar magnet exits the aluminum foil. And now the questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, we can tell that based on Ohm's law, the induced current would be large since we have 0 resistance, and this would make the magnet fall much slower through the tube. And what if there are holes or slots cut into the tube? How would this affect the ring currents in your model? We're using the same concept. This would effectively weaken the magnetic force applied on the magnet, and therefore the magnet would take less time to fall through the tube. Thank you for watching my presentation, and have a nice day.